This video will show how we can use a sampling distribution to estimate the mean of a population when we have the mean of a random sample from the population. We use the properties of the sampling distribution we know from the central limit theorem. Our example has a population of 10 employees. We want to estimate the average age of the employees. It would probably be easy to calculate the average in this case, but let's look at the process. We will take a random sample of 2 employees and take their average age. Here we have our 10 employees. We can calculate the population average, sigma, by adding all of the ages and dividing by 10. Our result is 380 over 10, or 38. Again, we know the population mean, mu, but let's work through the process to see what happens with a sampling distribution. For our random sample, we select Maria, who is 38, and Ian, who is 44. Now we can estimate the population average, mu, by using the sample average, x bar. Our sample average is 38 plus 44 divided by 2, or 41. Are we close? How many other possible samples are there? We can calculate this using combinations, and the result comes to 45 total possible samples for 2 employees. In an Excel file, all the possible samples were taken and the average of each of these were calculated. Then the mean and standard deviation of all 45 of these means were calculated. This is the sampling distribution, and the central limit theorem states that the mean of the sampling distribution is the same as the mean of the population. This turned out to be the case here. The standard deviation of the sampling distribution came to 5.448751. The central limit theorem also states the standard deviation of the sampling distribution, which is also called the standard error, is the standard deviation of the population divided by the square root of the sample size. So the population standard deviation is 8.173127. When you divide by the square root of 2, which is the sample size, you get 5.779273. That's not the standard deviation that was calculated from the sampling distribution. Have we proven the central limit theorem wrong? One of the assumptions made for the central limit theorem is that the population is very large relative to the sample size, or even infinite. If this is not the case, as in our example, we must adjust the standard error of the sampling distribution. Remember that the standard deviation of the sampling distribution is often called the standard error. The adjustment we must make is to divide the standard deviation of the population by the square root of the sample size, then multiply by the square root of the difference between the population size, capital N, and the sample size, little n, divided by the population size, capital N, minus 1. This last part, the square root of n minus n over n minus 1, is called the finite population correction factor. When we apply the FPCF, we get the standard error of the sampling distribution. Now, what does the distribution of all the means of all the samples look like? Based on the central limit theorem, as the sample size increases, the distribution begins to become a normal distribution. Let's look at the sampling distribution when n equals 2. Our population frequency distribution is skewed right, positively skewed. Our sampling distribution is also skewed right, but not as strongly as the population. Notice our sample of Ian and Maria. The mean of the sample is also marked on the sampling distribution. The n equals 2 sampling distribution is not perfectly symmetrical or perfectly bell-shaped, but it is closer to a normal distribution than the population. How about n equals 3? When we compare the n equals 2 and n equals 3 sampling distribution, we can see that the n equals 3 distribution is more symmetrical and closer to a bell shape. In this example, the population only has 10 members, so we will not get very close to a normal distribution. But in a large population, the greater the sample size, the sampling distribution will be closer to a normal distribution. By the time the sample size is 30, the sampling distribution can assume to be normally distributed. For n equals 4, notice the distribution is again more symmetrical and approaching a bell shape. So how does this help us? In our example, we have a sample size of 2 and an average of 41. How close is that to the population mean? We know that it is more than likely not the same as the population mean due to sampling error. X bar is 41 while mu is 38. How close is that? Our sampling distribution has a mean of 38 just like the population and a standard error of 5.45. How many standard deviations away from the true mean is our sample mean? Assuming the sampling distribution is normally distributed, we can calculate the z-score of the sample mean to be 0.55. That's pretty close to the true mean. And we can calculate the probability of getting a sample with a mean that far from the true mean of the population. In summary, our example shows how the central limit theorem allows us to use a sample and a corresponding sampling distribution to estimate the mean of a population. The standard error of the sampling distribution is the standard deviation of the population divided by the square root of the sample size. Sometimes the finite population correction factor will be needed to accurately calculate the standard error. The mean of the sampling distribution will always be the same as the mean of the population.